So let's talk about PMC surfaces or mushroom structures. Okay, PMC surfaces would look something like this. There's no real PMC surfaces, but we can mimic PMC surface. Okay, mimic PMC surface. And how do engineers do that? Well, this is two guys by the name of Steven Piper and Bolonovich. They were clever enough to actually come up with this surface that looks almost like a PMC surface. And let me see how to spell the names. The names are Steven Piper and Bolonovich. Okay, at the time when they were doing this, they were at UCLA. Okay, so what you do is to make a mushroom structure. And if you look at the mushroom structure, it consists of a capacitor cap followed by a stem, which is an inductor. So you can think of this as being very much like a LC tank circuit. Okay, there's a capacitor and then driven by inductors, and this is the ground plane, and then you will have inductors and then capacitor and then inductors and so on. So you can think of the circuit equivalence of this structure to be something like this. Okay, it would be something like this, and at the resonance frequency, then I is equal to 0. There's no currents flowing horizontally in this structure. So if I is 0, then Js on this structure is 0. It means that N cross H is approximately 0 on this surface because there's no current flowing there. So this is just what we need for a PMC. PMC is N cross H equal to 0. And you remember that for PEC, it is the other way around, that N cross E is equal to 0. So this structure, if you operate it at the correct frequency so that all these mushroom structures start to resonate, they form open circuits up at this surface. This surface would look very much like a PMC surface. So that's how engineers design PMC surfaces. Are there any questions regarding this structure? Okay, if no questions, then let's go to the image theorem for PMC surfaces. We have so far talked about PEC surfaces, and we figure out how to reflect images on the PEC surface by using simple image theorem. And we also did that for electric dipole as well as magnetic dipoles, okay, which is what we have here. Electric dipole, and then we have magnetic dipoles. Okay, these are magnetic dipoles. And then we try to talk about the construction of a PMC surface using engineering. And this is roughly the case of a PMC surface. Then let's go and assume that PMC surface exists. Of course, it does not exist in practice. It can only be engineered approximately. Then if you go and summarize the image theory for a PMC by duality principle, okay, if you have a horizontal magnetic dipole, then it actually should be negative of a horizontal magnetic dipole. Very much like the dual of this problem, that if you have a horizontal electric dipole, it reflects to negative of itself. Okay, here, a horizontal electric dipole reflects to the negative of itself. This is PEC surface. By the duality principle, a PEC surface becomes a PMC surface. So when you have this, you can see that this reflects to negative of itself. And then by the same token, if this is a vertical magnetic dipole, it reflects to something that is the same polarity as itself by the duality principle. And by the same token, if you go through the argument with the electric dipole, if you have a vertical electric dipole, then it will become the negative of a vertical electric dipole. And if you have a horizontal electric dipole, it is the same as its original self. So are there any questions regarding the use of image theory to find simple solutions? Okay, so if there are no questions, I'd like to move on to working on a case where we have multiple images. And if we can use multiple images to solve some complicated boundary value problems, such as this one over here. We have used image theory to solve a very simple problem involving, say, a positive charge over a PEC surface. And by argument, physically, we say that a positive charge has to see an image which is negative of itself. Okay, this is a PEC. And of course, if you have a PMC, the opposite happens. So if this is a PMC, you have a positive electric charge, then it should see a positive magnetic charge. Okay, and then you can do the same for a magnetic charges. Okay, so we're going only to talk about electric charges here. We're going to talk only about electric charges here, and then you can use image theory quite easily to say that if I have a positive charge, let's assume that this plane is infinitely long. Okay, this plane is infinitely long, and this is a PEC surface. Okay, then I can quite clearly see that the boundary condition is satisfied. If I have a positive charge, if I put a negative charge there, then n cross E must be 0 on this surface due to the fact that I'm just using image theory. But by symmetry, I can also see that this problem of putting the 4 charges in this manner also satisfies the image theorem for this surface over there. So I can see that n cross E is also 0 on that surface, which means that by the use of 4 charges, I can make n cross E over to be 0 over the entire angular surface or 90-degree surface I have here. Okay, so this is one use of image theorem that is beyond a flat surface. I can do the same thing for a more complicated surface like this one over here. And again, I can put this positive charge and negative charge there. And I put a positive charge and negative charge, and first think of a PEC surface over there. Okay, and then I can start to add, for instance, so if this set of charges, I can add the images, like I can add this one, which is the image to this one, and then I can add this one, which is the image to this one. And then I notice that I can add this one, which is the image to this one. Okay, then I notice that the boundary condition is also satisfied on this surface over here. Okay, and then I can see that the boundary condition is such that n cross E has to be 0 and n cross E has to be 0 on both these two surfaces. So by symmetry, you can see that by a judicious placement of the positive and negative charges, you can produce a problem where n cross E equals 0 on the surfaces that you have desired. Okay, this is only possible by using symmetry. So if the problem is not symmetrical, then there's no way you can find such a solution. Okay? So you can find a solution such as this one, you can find a solution such as this one, and maybe some other problems where you can have a certain degree of symmetry. Another problem that can be solved in closed form by image theory is this problem over here. And you can see that once I put a positive charge there, I have to use a negative charge if this is my only plane. And then I can also put in a plane here fictitiously to begin with. And if I were to put negative and positive charges over there, I can see that boundary condition on that thing is still satisfied. Okay, and you can keep putting images up and down. You can find that finally you will find that boundary condition is equal to 0 on both surfaces. Okay, boundary conditions will be 0 on these surfaces. Okay, so this is just a very simple use of image theory.